A warm welcome to everyone to this webinar covering electronics thermal management, how to simulate radiation heat transfer. Thank you all very much for joining us today. My name is Paul Lethbridge. I'm the Director of Product and Solutions Marketing here at SimScale, and I'll be your host today. Today's presenter is Alex Fisher. He's co-founder of SimScale, and he leads our thermal management electronics industry solutions effort. Alex has a background in computational mechanics and control technology and holds a diploma in mechanical engineering and numerical mechanics at TU Munich. So let's have a look at the agenda. So over the next 30 minutes, we'll start with a brief introduction to the application case study and the key design considerations. And then we'll get into a live demo of the LED heatsink. And we'll wrap up at the end. There are about 5 minutes left at the end for a Q&A session, and also give you the next steps so that you can try SimScale for yourself. Please use the chat panel to say hi, introduce yourself, and also feel free to ask questions using the question panel. And a reminder that your microphones will remain on mute during the presentation. And with that, I'll hand over to Alex.
Great, yeah, so also a warm welcome from my side. As Paul already introduced me, I'm working at SimScale as a product manager for electronics components, and you might have seen in the last couple of weeks that we had multiple of these webinars around heat transfer or different mechanisms of heat transfer, and we were looking into forced convection, natural convection, obviously including solid conduction in these cases, but we were kind of consciously leaving out radiation to give it a specific webinar, and this is now today this webinar where we want to really only look at thermal radiation, what's its contribution. Obviously we're going to touch the convection losses as well, because we want to see essentially what thermal radiation contributes compared to convective losses if it's switched on for different use cases. But the focus really is on radiation, understanding when it's needed, and also how simulation can help you to figure out, should you take into consideration radiation? Should you optimize your design by using, for example, radiative paints? So we're going to discuss all of these design topics, and also how you can apply radiation in your simulation, and how you can figure out if it's negligible or if it's significant and you should be looking at it. For that, we prepared a case study. You can see it on the right-hand side. It's a rather simple design of an LED with a metal core PCB and then just a heatsink. The heatsink has two different designs that we want to look at as well, but we're running simply conjugate heat transfer analyses here. So that means considering all mechanisms of heat transfer: conduction between the solid parts, convection around the solid parts, be it forced or be it natural convection, and we will be looking today specifically at thermal radiation. The design considerations that we want to look at for this purpose are 4 different things. Number 1, when is radiation even needed? So what would it mean for our design if we enable radiation, if we disable it, if you look at the results for these 2 simulations, and can we derive out of this essentially an understanding if we can kind of keep that toggle off, or if we should keep it on if we do further design iterations. Secondly, we're going to look at a surface finish. So we will use 2 different materials, or not really materials, but the surface treatment of aluminum, 1 times anodized and 1 times a specific radiative paint that allows you to have a very high emissivity value on these surfaces. As a third point, we're going to look at 2 different heatsink designs. I already mentioned this. I called it here dense and sparse. So essentially we have a heatsink. You can see it here as the third comparison on the right hand side. So we have one heatsink where we have a lot of heatsink fins, and they are very dense together, and we have one where we have a bit thicker but considerably less heatsink fins. And as a last consideration, we will look at the cooling strategy, so natural versus forced convection. The first three things are natural convection cases. I think I'm not telling too much ahead of the live demo that obviously natural convection cases, you have usually lower heat transfer coefficients, you have lower speeds, and that's why radiation has usually a higher contribution simply from forced convection just being more efficient in cooling in most cases. And that's why for natural convection cases, it's specifically interesting to look at the thermal radiation. We will also take a look here now, what does it really counter? What is the influence of radiation compared to the convection for the natural and the forced convection case? So we're now going to jump onto the live platform, and I will first show you our base setup. So we picked one as our base setup, and that is essentially the sparse heatsink. We will use radiative paint on the heatsink. We will use radiation and run a natural convection analysis. So these 4 parameters will be our base setup. From this base setup, we will always only change one parameter and then look at the results and get a feeling for how important radiation is, and also how you do it and how you set it up in the simulation setup. So let me now jump over to our platform. What you can see here is the SimScale environment. We are looking now at a result already of our LED device with a heatsink. We can see here visualization of the streamline, so of the natural convection air being sucked from the bottom to the top and cooling down these heatsink fins. That might be a familiar view for you if you are used to running CFD simulations. Not too different, I guess, from what you would expect. You have here different ways of filtering the result data, and that would be also the area where you would spend most of your time on SimScale, because this is the moment where you take your time to make a decision, to consider optimizations for your design and where you get the real value out of simulation. So I wanted to start by taking a look at this, but now we're gonna go back to the beginning. So how do you start on SimScale? Also looking a bit into the specifics of SimScale as a cloud native platform. And I will show you how to run a radiation analysis. And we will come back to the results section when we compare the different parameters later on. So let me go back to the geometry section. So there we can take a look just at the geometry model. We already have here flow region, so I'll just show you now the model again without the results in the view. We have here the LED chip, the metal forced metal core PCB, and we have the aluminum heatsink for this as well. And now we're gonna check, how could I even access this project, right? So you might have seen when I jumped out of the slide deck that I was just switching tabs from my presentation. And now you can see on top here an URL of simscale.com. So this is really the SimScale environment where you open up a project by a specific URL. So you also have a dashboard if you want to access it, where you can see all of your projects. And then if you dive into one project, you can do this by just opening up this project. It doesn't also matter where you located, which device you are using. You're just logging onto your account. So you can see over here my face. So I logged onto my account similar as you would do, for example, in your LinkedIn profile, and then I opened up this project and I have immediate access. It doesn't matter which operating system or which computer, or if I'm traveling. So I have access if I have internet connection and if I have a standard web browser. In this case, this is Google Chrome. So we're looking at our 3D results here. And I want to give you some more insights on why this is in some sense special. So if you look at the top, you also have this indication that my project is private. That might be a matter of course. So it should be clear that if I'm doing here sensible work and if I'm a paying customer or an employee on SimScale, that my project is private. But this indication is there because SimScale has next to its paying customers also a community that contribute to the data that is available on SimScale. So for example, to our templates or to our forum, to our knowledge base. And we have the possibility on SimScale to share content or collaborate on projects. And that's why it's always important to know what's the state of your project. And sharing means in our context that I can give full access to my project to other SimScale users. That might be, for example, customers of yours. They want to just see the result plots, how you verified that the solution is good enough. That might be colleagues of yours working in the laboratory. These people might then need only can view permissions that you can set here, or it might be colleagues of yours that want to use your input, your project as a template to run a new simulation, a new design iteration of a certain product. Then you can give them can copy permissions. Or if you're working with a colleague on a specific topic and you want to collaborate really on the project, then you would give them can edit permissions, and you can really work together on the same project. This same mechanism provides also a different advantage. So we have the possibility to share our project with support. And that means for us that if we run into troubles, if we are not sure how to model something exactly, and the perfect question might be now, should I consider radiation in my analysis? Then we can reach out to SimScale, to our support. And if we toggle on this share with support, then our support agents can see your project, they can jump onto your project and help you directly with the setup. So you would in this case also see then an avatar like you see on the top right appearing here, so that you always transparently see what is happening on your project. Reaching out to the SimScale support, the easiest works via this speaking bubble at the very bottom on the right. So you can open up here our chat and simply type a question. You get within a few minutes, no matter where you're located, an answer from our support agents. And you can directly discuss your problem. So you don't need to file some support ticket or anything like this. You get a direct answer. So in our case, if you really would want to know if we should be using radiation or not, we could just ask the support and get an immediate answer based on our setup or based on our use case. So much about some of the special cases about SimScale. We will now dive a bit more into how to set up this radiative simulation. So there will be more common ground to other solutions that you might have seen in the past. One common thing for sure is that we start very similarly. So we're bringing in a 3D CAD model to run our thermal simulation, and we can either do so by dragging and dropping or importing from our computer any CAD format essentially that is used at least for the electronics industry for 3D CAD. So if this might be SolidWorks, Solid Edge, Inventor, CATIA, etc. We read the native format. We also would ask you to, in normal cases, upload really your native files, because then we don't have the hassle essentially of dealing with different versions of files. You need to store multiple files. So just use really the native file. That's the easiest to do. You can upload this file, or you can use one of our partner platforms, like for example Onshape, to directly import a CAD to SimScale. If you did this, the CAD imports like you can see here. So we then have this model available in our 3D environment. We can now also make some modifications to the CAD model. So we can, for example, simplify complex shapes. In this case, for this heatsink, this is likely not needed, right? But you might have logos, imprints, etc. on the model that you rather want to remove, that are kind of easy to do, and you might want to prepare your model. So in this case, we created, for example, this out of flow box. So if I'm showing this again and maybe make this translucent, then you can see that we have here a flow box that helps us model or simulate the natural convection flow around the heatsink, and this was done in our CAD mode. I'm not jumping now into it, simply to focus really on the thermal radiation part, but please feel free, try it out yourself, and you can easily open up the environment just by clicking on the CAD model and editing it in CAD mode. Let me also quickly show you the different versions we're having here. So we've already seen now the sparse heatsink. Now we can take a look at the very dense heatsink. So really a lot more heatsink fins that we have for this model. The height of the model is the exact same. So we try to not change the surface area. If you look from a projected view onto the heatsink, then this is the exact same, but we have a lot of more heatsink fins in this dense model. And we have here two additional versions of the same CAD files. For the forced convection case, we simply put a flow channel that pushes air around the heatsink. So we just put a standard cylinder around it to mock the forced convection flow around these parts. Great. So if you stand at this point and you want to simulate now, you create a simulation by opening up our analysis type choice. You can see here the different physics that we can simulate. They are grouped as flow and structural. So there's a lot of different analysis types that you can run if you want to. If you don't know exactly, you can also use this little tool where you can see which kind of simulations do we want to perform. So we want to include flow, we want to include heat transfer, and this both for fluids and solids. And now we know which analysis types actually allow us to do so. So we can then create a new simulation from it. I'll do this here quickly. This is now created on the latest geometry that I imported into SimScale. So right now the contact detection is running. We don't need to really look into this in detail. But what you can see here is that you now get a navigation tree, a simulation setup tree, if you will, where you define all of the important parts that are important for your setup. There's two different points that are important. Many of these you can see already have a green check mark, like initial conditions, numerics, the mesh settings, etc. So for these settings, we provide default values also based on the data that we can generate from our community to provide you with a good default solution. We keep these settings for you to change. So some experts really want to optimize the last little detail or customize the settings to their exact use case. This is always possible, but it's not required. So you don't need to touch these settings. You can concentrate on the expertise that you have about your own application, and that is usually defining the material properties that we have, defining the boundary conditions, and defining power sources, for example, in a heat transfer analysis. How this looks if this is completed, I can show you here. So let's open up now our base setup, meaning natural convection of the sparse LED heatsink. We can check again here the geometry. What did I do? So I put here some materials in. So we have as fluid our air volume. We have this here called aluminum enforced PCB board. We have the aluminum with radiative paint for the heatsink, and we have silicon simply for the chip. You can see that there's also the anodized aluminum, in this case without any assignment. So I already created these two different versions of the aluminum material with different surface treatments so that we can later on compare them. But in our current setup, this is ignored, this is not taken. For the boundary conditions, we can show again the flow region. We only have one boundary condition that matters, and that is natural convection inlet outlet, meaning an open environment, simply free convection around our part. That's quite easy to be done. And that's essentially everything I need to do except for adding the power source on the LED. In our case, this is 10 watt, and my setup is completed. So far, we didn't do anything for radiation. So you might be wondering if you're running it without. We don't do this. The radiation is toggled here on the top level of the analysis type, and we don't need to make any specific changes or any special changes. The only thing we can do if we want to is that under numerics, again, we can here use an expert feature, essentially, the resolution of the radiation. By default, this will be moderate. And this just defines how many rays essentially are used for the numerical method to compute the thermal radiation accurately. Usually you don't need to take care of this, but I wanted to mention it nevertheless. Good. That was an impression of how you set up a simulation on SimScale in general, but specifically now considering radiation. And we will now take a look at the results as well. So first, if we take a look at results, we can either do so by looking, for example, at 2D plots. So here you can see, for example, the temperature. The solution is meanwhile converged. This is obviously a steady state case. And you can see the final temperature in Kelvin that we get for the bottom surface of the LED. So that is easy to compute. We can also see the watt per square meter radiative flux that we have on this surface. And what I added as well is here an area integral on all surfaces that radiate. I already opened this here to keep the other view a bit cleaner. So you can see here that on all of these surfaces, we can see now the radiative flux as an integral value. We get the total wattage that is that you get from this. And these two values, or these two curves that you can see here, those are the bottom and the top surface of the heat sink that radiate by far the most. Almost 10% of the full radiation contribution comes from these surfaces, and all the other ones have a much lower impact. The reason for this, I guess, is quite obvious. We can again look into our results, our 3D results for this. If we open up the results again, we see essentially that most of the LED heatsink fins, as it's a radial setup, if you will, that most of these have neighboring heatsink fins, and most of the radiative heat flux that goes out of them will be consumed or kind of will be absorbed by the opposing faces. So we just have a small net radiative loss from these faces to the outside. In total, obviously, we have some, right? If we again look at the projected surface, and we have this big contribution from the top and bottom surfaces. We now also want to take a look at the results for different materials. So that was at first looking at the radiative results. We have for this radiative paint, which has an emissivity of 0.95, I believe. Let me open up the settings again here. Yes, we have here the emissivity of 0.95. We have for the anodized aluminum 0.7. So if we open up again those results, we will see here a maximum temperature of 46.9 degrees Celsius. And if we open up the same simulation setup with a different emissivity, we will see that this is a bit higher, simply because the radiative loss that we could use in this case is less. We have 47.7 degrees in this case. So that is, if you look at it, just a bit more than 1.5, I believe, degrees more. That's simply because of the different emissivity. So you might also wonder, would have been maybe also okay to not include radiation at all. And this is the next result that we want to look at. So take into consideration, or keep in mind, we had 46 and 47 degrees on the LED chip now for the two radiative cases. And now I ran the same simulation again, now completely toggling off the radiation, and I'm at 52 degrees. So now I'm about 20% higher. The surrounding temperature that we have in this case is 20 degrees. So if we take this as a base for our temperature difference, then we have 20% higher temperatures, and that's quite significant. So obviously in this case, where we have such a high emissivity on our main component or heat loss component, the heat sink, and where we have free convection to the outside, it's very important that we toggle on the radiation. And if you would have run now such an analysis, we would definitely keep it on when running further design iterations of this model. If we would run a forced convection simulation, though, this might look a bit different, and that's what I want to show you as the last comparison. So if I'm opening up now the results that we have for the forced convection analysis, then we will see, if we show also the temperature and the parts, we will see that we are at 25 degrees. So we are on an 80% lower temperature compared to the 46, 47, because in this case, we are really using velocities of, let me hide quickly the parts. Velocities within the heatsink fins of about 4 to 5 meters per second. For convection, for natural convection cases, this is usually something between 0.1 to 0.5 meters, so much lower velocities that we get from natural convection. And in our case, quite interesting, we will also see this when we summarize the result. The dense heatsink even allows less natural convection to happen. So for the natural convection cases, our cooling is better, considering the the sparse design. For forced convection, it's the exact opposite, because we can ensure by pushing so much air through the heatsink fins, by forced convection, we can make sure that all of them are well kind of served by convective flux, and that's why the dense heatsink then has a better performance for us than the sparse heatsink. I can also show you this if you will. So if you open up the dense heatsink with radiative paint again, we will see that our temperature will be here almost around the temperature that we have for the sparse heatsink without even considering radiation. And here I showed essentially the velocities in the same scale as we had it for the natural convection case for the sparse heatsink, and you can see that we have really low velocities here, so 0.1 or even less meters per second of flux, convective flux, that we get for these models, and our temperature as a resulting field is at 53 degrees. Good, that was a lot of information summarized here in these on the platform. I'll quickly jump back and very briefly give you an overview on this slide. So just running through what we just saw on the platform. We have now our base setup, again, natural convection of a sparse heatsink with radiative paint. That's our first 2 column charts or bar charts. And we have here the maximum LED temperature that we got, and we have the radiative heat loss contribution. So how much of the 10 watt power was lost via radiation? All the rest obviously is then lost via the convective heat loss, as we have a free floating domain. Good. Now, in our case, this is around close to 30% contribution of radiative heat loss, so really a lot. If you don't enable radiation, obviously we have 0% radiative heat loss contribution, but also a much higher temperature. For the anodized aluminum, we have a lower radiative contribution, but also just a little bit higher temperature compared to our radiative paint setup. So also that is likely expected. For the dense heatsink, it's really interesting that we have such a high temperature, but that is simply because the velocities are so low for the natural convection case. For forced convection, it even performs better than our first design or our base design. And now, very important, if you're running maybe a forced convection case, that might be not always the case, but you can easily test it on SimScale. We have a much lower temperature. You can see like a bit over 20 degrees Celsius. And you can see that now our forced convection heat loss contribution from radiation is really low. So we're here talking about 2.2%. So in this case, you might really consider not even running with radiation if you're looking now at more design considerations, or you might even run it just as a last validation step when you're done with your design work. That's as much as I wanted to tell you about radiation today. If there's any questions, please feel free to ask. And I'm giving back to Paul to summarize also how you can access SimScale and how you can do this.
Thank you very much, Alex. So we have about 3 or 4 minutes left for Q&A. We've had a few questions come in on the chat. I'm going to select just a couple of them because we just have a few minutes, Alex, and I'll let you answer them, okay? So let me just have a look here. Okay, so what is the typical time frame for a heat transfer simulation that includes radiation?
Okay, yeah, then if that's the case, let's really briefly jump back again. Let's look at the base setup, right? Because that's where we've spoken most about it. So in our case now, we ran this for 88 minutes, 23 core hours. The core hours are just how kind of we do the calculations on SimScale. You can already imagine that we did not run this on one core, but that this was now a more powerful machine in the back end, as we're running all of this in the cloud, and we can also obviously run it in parallel, but I guess that answers the question. So this ran for 90 minutes to be finished.
Excellent, thanks, Alex. A very good question here from Clement. If you needed such a heat sink to operate in a vacuum, how could SimScale be used to offer insights on how to redesign it for greater radiation loss?
Well, yeah, that would be, in this case, you would not model the fluid, or would model the fluid essentially by mocking some material parameters that there would be nearly or no convection happening. And there we would only have conductive losses in case you have a boundary or this is mounted somewhere, and you would have additionally then the radiative losses to the ambient. So in this case, we would really switch off convection and only run conduction and radiation, but also this happens in some cases. You could also consider then running an FEA analysis though, right? Because if you're not solving the flow field, you might be running a finite element analysis instead, as it's usually computational wise less costly or less resource heavy.
Lovely, Alex, thanks very much. Well, we're pretty much out of time. I'd like to get you to the next steps so you can understand how to sign up and use SimScale for yourself. Alex, if you can move to the next slide.
Oh, yeah, sure.
So, yeah, so thanks. So, I mean, I hope you all found the webinar pretty valuable and you're now really keen to get into it and start using SimScale yourself. So the way to sign up is you basically go to simscale.com and there's a sign up area there showing, you can see the link on the slide there. You can also request a demo, so you can contact us directly and you can get a one-on-one demo. So you go to sales@simscale.com and an application engineer will be in touch with you within 24 hours. Also, a link to the recorded version of this webinar. If you have colleagues that missed the webinar or you wanted to share it, a link to this webinar will be made available to all participants and all those that registered. So with that, we're just a little bit over the bottom of the hour here. So I want to thank you again, Alex, and also thank our attendees. So with that, that brings us to the very end of our webinar. So thank you again.